So chapter 9, the new chapter we're starting this week, talks about nonlinear systems. But in order to warm up our way into that, what we're going to be talking about is equilibria of nonlinear systems. And I'm actually going to be a bit vague about why we're going to be talking about actual linear system during this week instead. So we're going to start about nonlinear systems of ODEs. That is that we're looking at a function y, function of t, and when you compute y at a given t, you have a vector. So yt is a vector in R. So n components of y. That means that the derivative of y prime, derivative of y with respect to t, is also a vector. So if we have dy over the t equals f of y, it means that f takes as input y, a vector in Rn, and returns something that has the shape of y prime. So again, a vector in Rn. So we write it this way, f going from r to the n to r to the n. It takes a vector in Rn and returns a vector in Rn. In the cases we have seen until now, f of y was a matrix multiplication with y, so a times y. That is a proper way of doing it. If A is a square matrix n to n, you can look at it as a transformation that takes a vector in Rn and returns a vector in Rn. So that works in this setup. In the next weeks, we're going to start considering the situation in which f is not linear. So a times y will be the only linear situation we have considered, and now we start considering situations that are not linear. The first thing we do when we are faced with nonlinear ODEs, and this is true across the board, whatever nonlinear ODE you want to talk about, the first step is always the same. The first step is studying equilibria. So finding a vector y in Rn such that its derivative is equal to 0. That means finding y such as f of y is equal to the vector of zeros in Rn. If that is true, then y prime is equal to 0. That means that if you start at y in your ODE system, is y as your initial condition, you're going to stay there for all the times. This is an equilibrium. And what happens is that we're going to be more clear next week about it, but the behavior next to an equilibrium is similar to the behavior of a linear system with constant coefficients. The idea is that if you're close enough to the equilibrium, the only thing you notice is something constant, and it behaves like a linear system. But again, this is a bit hand-wavy, and it's got to be made a bit more precise next week. But this justifies going back and reviewing all the type of equilibria that we have seen in the context of linear systems. We're going to look at 2D linear systems with constant coefficients. This is during chapter 7, we have seen linear systems with constant coefficients. And now we focus a little bit more on 2D just because it's easier to plot. It makes for nicer plots because we don't have to handle 3 dimensions. It is possible to extend all that we have seen, that we are seeing in 3 dimensions, but it's just cumbersome to plot it, so it's less graphically available to us. And 2x2 allows us to give a full characterization of everything that is happening, and it's short enough to be condensed. So we have a matrix, an ODE of the form x prime equals a of x, and the matrix A that is A, B, C, D in a 2x2. So we assume we're able to compute the eigenpairs. In a normal situation, we have lambda 1 xi1, lambda 2 xi2. We have seen that sometimes we don't have the normal situation, so we don't have the second eigenpair. But let's assume we have lambda 1 xi1 and lambda 2 xi2. Then there are some options. And the options that we're interested in are only options about lambda 1 and lambda 2. Because the eigenvectors just give us some information about in which directions things are happening. They don't give a lot of information about how things are happening. So we concentrate, when we talk about 2D linear systems, linear system ODEs, we concentrate on the eigenvalues of the matrix we are referring to. And the options are limited. Either the eigenvalues have the same sign, or they have different sign. They can be equal, or they can be complex. We also have the situation in which we don't have two eigenvalues. So let's go through the review of all these situations in the most compact and fast way possible. So the first case is we have two real eigenvalues. They're different, and their product is positive. If the product is positive, it means that they have the same sign. I'm not specifying the sign yet. It can be the case in which you are talking about positive sign or negative sign. I don't care yet about it. So in this case, the solution, the general solution for this situation is the linear combination of the eigenvectors multiplied by the exponential of the eigenvalue times t. So this formula that by now you should know by heart, c1 xi1 e at the lambda 1t plus c2 xi2 e at the lambda 2t. Notice that since only xi1 and xi2 are vectors, the ordering doesn't matter. If we consider lambda 1 and lambda 2 negative, we could be considering both of them positive, but let's start with the negative case. If they're both negative, what it means is that the exponentials of lambda 1t and lambda 2t both tend to 0 for t tending to infinity. That means that over time, x, the vector x depending on t, tends to 0. We call this a sink or a nodal sink because wherever you start in R2, you're brought to 0, 0. And then the question is like, how does it go to 0, 0? Well, oh, maybe this slide could have fitted better later. But as a side remark, I'm concentrating on lambda 1 and lambda 2 positive. But what happens when we flip? Instead of considering t, we consider minus t. In a certain sense, this is going back in time. Instead of growing t, starting at 0 and going towards plus infinity, we start at 0 and we go towards negative infinity. We try to see what is the backward history of our point. Then we can compute x at minus t, and that means just replacing t with minus t in our expression. And we can therefore change, instead of writing exponential of lambda 1t, we can write exponential of minus lambda 1t. And the same for lambda 2. So we can replace lambda 1 with lambda 1 hat, and which lambda 1 hat is minus lambda 1. That means that we can, instead, when we are changing time, what we're actually doing is changing the value of the eigenvalue and changing the sign. This means that we can actually just consider the situation in lambda 1 and lambda 2 are negative and know that once we find the trajectories, the behavior of x for lambda 1 and lambda 2 negative, we know the trajectory for lambda 1 and lambda 2 positive because it's going back in time. So now we have x as linear combination of the exponential of lambda 1 and lambda 1t and lambda 2t, each multiplied with the associated eigenvector. And here I made a mistake. We're choosing lambda 1 smaller than lambda 2 smaller than 0. It's an ordering option, so we can flip them just by ordering them in a different way. So this is not restrictive, but we're choosing, not as the slide is saying, we're choosing lambda 1 smaller than lambda 2. If we do that, then we can take lambda 2 out, exponential lambda 2t out of our equation, and then we have exponential of lambda 2t multiplied by c2 xi2 plus c1 xi1 exponential of lambda 1 minus lambda 2 times t. Lambda 1 minus lambda 2, so lambda 1 is negative and it's smaller than lambda 2. minus lambda 2 becomes positive, so lambda 1 plus absolute value of lambda 2, but we have chosen the absolute value of lambda 1 to be bigger than the absolute value of lambda 2, not as written in the slides. So the exponential of something, it's negative times time. That means that that element is tending to 0 over time. That means that our parenthesis for t tending to infinity tends to c2 psi 2. So for t tending to infinity, x tends to c2 psi 2 times exponential of lambda 2t. So we have something that depends on time, c2 exponential of lambda 2t times psi 2. So for t tending to infinity, xt is parallel to psi 2. So we have psi 1 and psi 2, and for t tending to infinity, so for t very large, xt is parallel to psi 2. So it's squished in that direction. All points, they start wherever, but at the end of time, they're parallel to psi 2. So a point that is somewhere else is first going along, like almost parallel to psi 1, and then be dragged in by psi 2. And the same is true for any point that is not in the eigenvector, a multiple of the eigenvector itself. So if we fill in, we fill something like that. If you're exactly on the eigenvector, you're going towards 0, 0. If you're away from it, you go first fast to 0 with the lambda 1 that is in absolute value bigger than lambda 2, and then along psi 2. Note how this is a portrait of what happens of any point that starts anywhere on R2 and gets moved by the ODE we just chose. We have lost, though, the information about time or speed. So we don't know if some points here are going faster than others or slower than others. We just know that over time, wherever they start, they move towards the center in a certain way. What we are plotting here are trajectories. So we can imagine that each one of this is a grain of sand that is moving over time, and this grain of sand is leaving a trace. This is what we are seeing. We don't see how fast or how slow that grain of sand was going, but we see the final result of where it went. This is what a phase portrait represents. An information about how things move, where they go, not how fast or how slow they do that. An important thing about phase portraits, in any dimension, but again, dimension 2 is the one that is easiest to plot, so the one we will be plotting exclusively, is that they are continuous. What does that mean? It means that things need to be smoothly changing from one point to the next, at least locally. So if you start next to a line that has been drawn, you expect to be following the line that has been drawn. This makes our job of plotting things easier because there is no break in the situation. There is no suddenly something that starts moving the other direction for a reason. If there is something that moves in another direction somewhere else, there must be some connection between here and there that allows it to move that way. This is something that helps us a lot when talking about phase portraits, this sort of continuity. So we can look at each component of the solution. So we can split our x of t into two elements of the vector, so x1 and x2. Each one of them decreases as a double exponential. And we can check a MATLAB code to see how they change over time. This is very similar to the MATLAB code you have written for Lab 4. We're just going to be testing different cases in there and see what happens. I've written a little code that I called plot trajectories, and I'm going to be sharing with you, in which you can choose lambda 1, lambda 2, and psi 1 and psi 2. So you're giving the code the eigenpairs, and it automatically plots the behavior of the phase portrait depending on these values. So here I chose lambda 1 and lambda 2 being both negative and some eigenvector that I chose. What is important? It's important the sign of the lambdas. The eigenvectors we can choose to make pretty plots, but the behavior will depend on the signs of lambda 1 and lambda 2. And I'm going to run this, and this is what I'm going to be seeing. I could plot it a bit thicker next time, but you see the two eigenvectors drawn in green and the trajectories of the various elements that started around the center and that moves towards the center. And because the eigenvalues are quite similar, what you see is that they're bending towards the slow eigenvalue and eigenvector is not very steep. But if I were to change one of the two lambdas to be much smaller than the other, then you see that the dynamics is much more squished towards one of the eigenvectors with respect to the other. Because there is one direction in which things move very fast, the exponential of minus 5t, it's dragging things very fast towards the center, while the exponential of minus t, that is the other eigenvalue, it's not that fast. So you first squish towards psi2 associated to the slow eigenvalue, and then you move slowly towards the center. Similar behaviors we would see if we change the sign. So here I just flip the signs, but the behavior that we see, the trajectory, is the same. So here, because in MATLAB it's a bit hard to draw arrows, there is no directionality of this plot. We just know the trajectory. So we have to fill in ourselves if we know that things are moving towards the center or away from the center. And here you really see how changing the sign of the eigenvalues doesn't change at all what we are seeing at the end of the day. So the trajectories don't depend on the sign. What depends is if we're moving towards the center or away from it.